pull up. All right. Welcome back. Happy Monday. Good to see you guys. Take out that homework 2.6a from last week because I went through it and there was some good stuff, but also some stuff that it seemed like we might have been struggling with. So I put the answers right on the announcement for today. So we just take a look and go through them, make sure you're feeling okay with them. And then we'll add a little something to it today. And hopefully, I mean, I'd love to get a chance to even practice this stuff while we're here. But you really have to make sure you've got this stuff down and that you're starting to be able to do it without looking back at notes, because we're going to wrap stuff. I'd really like to wrap this chapter up like by early next week and take a test before next week is out. Okay. I'm thinking like Wednesday, Thursday of next week would be a great couple days to get this done. So if we can take today, thank you for being here virtually. Take a look, make sure you get it, okay? The idea is always going to be the same with all of these. Factor and simplify first, and then let's figure out what numbers don't work. All right, and with number one, there's really nothing we have to do. It's just already factored and simplified. So we just look at the denominator and we figure out what numbers don't work, and that's going to be -3. And because that was only a 0 from the denominator, that's your vertical asymptote, not a whole. Cool. And the process just repeats and repeats and repeats. Nothing really has to change much about what we need to do. It just depends on what we've got. Factor the denominator for number 2. Nothing to simplify. So those are going to be your 2 excluded values. And really just want to think of it as your domain, right? X just can't be -1 and 1. And whether you use the set notation or not, totally up to you. But when I write my vertical asymptotes, I want to write them all separately. Like, don't write them together as one thing, because you have 2 different lines. Like, we're going to draw these dotted lines, these dashed lines at both of those spots. So x equals -1, x equals 1 are both going to be vertical asymptote. And because we didn't divide anything away, there aren't any holes. Okay? And it's just whatever you've got, you just have to be able to factor it, right? Which is why we spent so much time factoring, because now we're really going to need it, right? Because with number 3, you got 2 different kinds of factoring. And there's no GCF, so I always look for that first, but there's nothing there. So different squares on top and then just quadratic trinomials on the bottom. But you had an x minus 2 and an x minus 2, both top and bottom, so we divide those away, which gives us a nice, simpler function to look at. But both of these are still numbers that we want to make sure we write down as part of the domain that just doesn't work, right? -8 and +2 not going to work. But because we divided away that x minus 2 factor, that's not going to be a vertical asymptote for us. It's going to be a hole instead. So vertical asymptote only at x equals -8. And then a hole at 2 comma below something, right? And to figure out what that is, you just take that 2 and you plug it into the simpler version. So I just kind of like at the bottom right there, just kind of rewrote x plus 2 over x plus 8, dropped into 2, and simplified 2/5. Okay. And you want to write your hole as a point, right? The vertical asymptote is a line. The hole is a point that we're going to like draw a big old empty spot. Okay, 4, just try to make it just a little bit trickier in terms of the factoring so that you can get used to it. There's a GCF on top, right? You can take out the 2x, you have x plus 4 left behind. And the denominator is the sum of perfect cubes. And I saw a lot of people not factor that denominator correctly. So if you didn't, fix it. But know that because you're just taking x cubed and you're either sliding it up or down, right? So x cubed, it looks like that, which will only ever have one x-intercept. If you add a perfect square to it, or you subtract a perfect cube, sorry, or subtract a perfect cube from it, you're just doing a vertical shift. It's only ever going to have one real x-intercept, whether you put it there, right there, doesn't matter. Right, you're only ever going to have one x-intercept. So I went through the process of checking the denominator. I checked the discriminant to see if there was going to give me a real answer. There won't ever be. There won't ever be with that second factor right? A plus B, A squared, AB, B squared. A, B, A squared, AB, B squared. And with same opposite, always positive with the sign. Okay, now some of cubes and difference of cubes doesn't come up a ton, but we got to keep that stuff fresh. So I'm going to try to throw that at you every now and then. But once we do factor the top, factor the bottom, we've got something we can divide away, right? The x plus 4 over the x plus 4, those go away. So that's going to be the only excluded value because nothing here is real. Never will be. So you never have to worry about it. Okay, it's only going to be that first factor that gives you an x value to keep track of. But because that was the one we divided away, there aren't any vertical asymptotes. It's only going to be a hole at that spot. Negative 4 comma something. So what do? I take that negative 4, I go back to the simplified version, I drop it in, and I see what it gets. Kind of gross, negative 1/6, which is what it is. Okay? It's a lot to start remembering. Okay, and if you know that Wednesday, Thursday next week is when this stuff is going to be tested, you gotta start committing this stuff to memory. You're actually gonna have to start studying math. I know we haven't really done that this year because everything has been open notes, but I'm giving you now more than a week's notice that that's when our test is going to be. You're going to have to start preparing, and it's going to be lots to remember. Okay, that's only second half stuff. 2.4, 2.5, 2.6, and 2.7. Okay, nothing polynomials, but obviously polynomials are a big part of that. So you want to start to get yourself ready, get yourself comfortable, which is by probably the end of this week. I'll have a study guide for you and a nice kind of list of those topics that are going to be on there so you know what you need to do. Okay, because I'm hoping by the end of this week we'll be done, and really we'll just take kind of Monday, Tuesday to prepare, maybe a little review. And then Wednesday, Thursday, you'll have that two-part, probably what I'm thinking, two-part test, one in class, and then something else. Okay. Okay. If you are at home, go to today's announcement and click on the presentation for today. I'm going to stop sharing though so that your video doesn't have that big screen looking at something. I want to be able to show you what's going on. Okay. And this is what we kind of ended with Friday. Okay. I honestly think you guys should probably have this stuff written down somewhere. If you did it Friday, great. But if you haven't started to write down what happens at the ends, right, this is the last thing from Friday. Looking at behavior, right? We've got everything else covered so far with things that don't exist, right? We've got all of the vertical asymptotes figured out. We've got all of our holes figured out. And before we start plotting actual points, we need a direction for where those arrows are going to go, and kind of like what we did with asymptotes, with polynomials, right? We started to graph x-intercepts, great. I'll show you how to do that this week, Wednesday, Thursday. But I want to talk about end behavior first, okay? And so when we're looking at the end behavior of a function, I'm going to point you guys in this direction for now so you can see me talking about it. I'll get closer. What really happens with us with end behavior is we start to look at what happens when x gets really, 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 really big. Right? Because that's all end behavior is. What direction my arrow is going to be pointing on the left edge and the right edge. So what happens when x approaches, that's that arrow, right? Positive, negative, infinity. It's really just dictated by just that. What happens when we plug in really, really, really big numbers for x? And if I look back at some functions that we looked at last time, right? This is what we did on Friday. When I think about plugging in really, really big numbers for x, it doesn't matter what it looks like, right? I'm talking really big, billions of billions, right? Billion to the billionth power. Subtracting 9 from that isn't going to make a difference. Subtracting 12 is not going to make a difference. And even subtracting x, like take a billion to the billionth power and square it, and then take a billion to the billionth power away from that, this is still going to be in control as to how far we're going to go, what direction we're going to go in. And so what I want you to really think about when we're dealing with what direction your arrows are going to be pointing in is just look at the largest power, top and bottom, because those are going to take control. Okay, and so there's really a couple possibilities, 3 of them. If your degree on top is smaller than your degree on bottom, okay, like number 1, right? Degree 0 over degree 1. Your denominator is going to grow really, really, really fast. And if your denominator is getting really big, that means your fraction is getting really small, and we are going to head towards 0. Okay, so if your degree on top is smaller than degree on bottom, nothing else matters in terms of end behavior. We're going to draw a horizontal asymptote that is the x-axis, okay, the line y equals 0. Because that's where your numbers are going to go, where your y values are going to go, because denominator is huge, numerator can't keep up, so we're going to head towards 0. Okay, if your degree on top is the same as your degree on bottom, then as you plug in numbers for x, they're just going to grow at the exact same rate. Nothing is really going to change when I start plugging in a million or a billion or a trillion. Doesn't matter. The degree of the top being equal to the degree on bottom shows kind of that, you know what, it's really not going to matter what those x values are. They're both going to head towards the same thing, but you might have a number attached to that largest power of x, and that's what's going to take control. Is that your horizontal asymptote is going to exist at y equals the ratio of those leading coefficients. Now maybe they're the same, right? Maybe it's x cubed over x cubed. So 1 over 1, okay, so we'll go to 1. But if it was like 2x to the 5th over 1x to the 5th, right, that's going to make a really, really big difference. Somebody's saying the audio is terrible. Hold on, let me see if I can fix it. Okay, let me turn it off and turn it back on. It might do. How about now? Is this better?
Yes, it is.
Yeah, okay, good. Sorry. Okay. I didn't say anything you missed. It was really just, we're just looking at that slide on the presentation. Sorry about that. Okay, so if degrees are the same, it's always going to be the ratio of the leading coefficients, okay? And if the degree on top is larger, because that's the only other possibility, if you got this really big power of x, and the one on bottom is just, it could be 1 less than that, it could be 2 less than that, doesn't matter. If the difference, right, is positive, right, we got a degree on top that's larger, we're not going to head towards a specific number because your fraction is getting bigger and bigger and bigger and bigger. But there is going to be an asymptote that we're going to follow. Okay, it's just not going to be horizontal. It's going to have a slant to it. Okay, and there's another word that means slant, and it's the word oblique, which really just means slanted, right? Not heading towards anything. Okay, this is the one that takes the most work. And so this is the one that we'll probably see the least. We're not going to run into these a ton, but we will see them today, and you'll see them for sure moving forward. But if we actually want to find the line, or you're going to see it could be curved, it's y equals to the actual quotient. Like you've got some rational function. So what do? We'll actually divide them. We'll do polynomial long division. We'll do, if we can, synthetic division. And it's just y equals the quotient, no remainder. Okay, we leave the remainder off because that's actually going to be the distance away. We don't have to worry about that. That would be super, super tough to do, to graph this curve, graph this slanted line. The perpendicular distance from the graph to that line is the value of the remainder. So what's going on there? For us, I just care about actually dividing this stuff out. Okay, so have this idea so you know what to do. Because all I want to do first is deal with end behavior. I don't want to do anything else yet with these functions. Because there's a bunch of them, and some of these I didn't make them work out all that nice. I just want to work through these 7 with you. Right here, right now together. Then I will pull up homework 2.6b that takes you through all of it. Okay? Factor and simplify. Domain, which is what I'm going to start calling it because that's really all it is when we talk about excluded values. Vertical asymptotes, holes, and then end behavior, okay? So I'm on the next slide if you're at home, okay? Let me get my stack book so we can get more to eye level. A little better. Oh, that's perfect. Okay, cool. And so what I want you to do is write these down. It's going to take a little while, okay, to write them all down, but just give yourself a space. 1, 2, 3, 4, 5, 6, 7. And we're going to go through this process of how to find either a horizontal asymptote or a slant or oblique one. Those words are interchangeable. You don't have to use both. You just have to use one. Slant is kind of the informal one. Oblique is just a fancier version of that. It literally just means, like, if you like typed in oblique definition, you would find it just means slanted. Okay. So take some time, write these 7 down, because I want you to have them, and then we'll go through the process of how to figure out, do you have a horizontal asymptote or a slant one, okay? 5, 6, and 7 are going to be the ones that need more space. 1, 2, 3, and 4 are going to be super fast. Like, you can just put like 4 lines, four functions, and you'll be good, okay? But I want you to have them down so you're not writing them down while I'm talking. So take a minute, just write these down somewhere. And all we're going to do is find end behavior, which is really just, does it have a horizontal asymptote and where? Or does it have a slant asymptote and where? Like, super fast, super easy for those. But then 5, 6. Well, I'm just going to start with 5. We'll do that. Okay, cool. All right, so just end behavior. And remember, when we're talking about end behavior, all we have to do is compare degrees. And because we're talking about horizontal lines or slanted lines, they're all going to be just y equals something, right? Vertical asymptotes are always going to be those x equals. But for us, when I look at f of x, and I'm thinking about what kind of direction I want to point my arrows in, I just want to compare degrees top and bottom. So what's the degree on top if it's just a constant? 0. What about on bottom if it's linear? 1. And so if you've got a degree 0 over a degree 1, the degree on top is smaller than the degree on bottom. So what y value are we always headed to? Good. Doesn't take any work. Just takes a minute to think about it. Good, Ethan. 0. Y equals 0. All right, number 2, going across there, g of x. x plus 3 on top and x squared plus 5x on bottom. And we could do lots of stuff, right? We could do everything to this function, but right now all I care about is end behavior. What's the relationship between the degrees? Good. Denominator is bigger, right? Denominator has a value of 2 for the degree, numerator has a value of 1. So if the degree on top is smaller than the degree on bottom, what y value are we headed towards? Always. Don't have to think about it. You just have to understand that relationship. Y equals 0. I mean, all of these. I can just put y equals y equals y equals y equals for this end behavior. All right, number 3. X squared minus 9 over x squared minus x minus 2. What's the relationship between the degrees? They're the same. And so if they're the same, when I start plugging these really, really big numbers, they're both going to grow at the same rate. And subtracting 9 and subtracting x minus 2, that part won't make a difference when these numbers get really big. And so if the degrees are the same, what y value are we going to be headed towards? The ratio of the leading coefficient. What's the leading coefficient up top? 1. What's the leading coefficient on bottom? So what's 1 divided by 1? There's a horizontal asymptote at y equals 1. Guaranteed. Okay, what about number 4? What's the degree on top? What's the degree on bottom? They're the same, right? And so if my degrees are the same, all of the rest of that stuff afterwards, although it's obviously going to make a difference as our numbers are kind of small, when the numbers get big, it won't matter. And so all we have to do is take the ratio of those leading coefficients. 6x to the 4th divided by 2x to the 4th, really just the 4th 2, 6 over 2. We have to do is divide those leading coefficients. What's 6 divided by 2? There's the horizontal asymptote. Y equals 3. The concepts aren't hard. There's just lots of them. That's, I think, what makes this chapter a little bit trickier is there's lots going on, and you have to know what to keep track of. Okay. Number 5. This is where things get a little bit trickier, right? Degree on top is 2. Degree on bottom is 1. If the degree on top is larger than the degree on bottom, do we have a horizontal asymptote? What do we have instead? A slant asymptote or an oblique one. How do we figure that out? How are we going to figure out y equals something? What's the process? Because this is the only one that's actually going to take some work. Here, we actually have to divide. We have to figure out what happens when I take that numerator and divide it by that denominator. Okay, and I'm not talking about factoring and simplifying, although that might be nice if it could work out that way. But in a case like this, where there's no factoring the numerator, we really just divide. And because we have a linear denominator, we actually have some choice. We could do polynomial long division, or we could do synthetic division. And when we set up polynomial long division, it's just, all right, the numerator goes on the inside, the denominator goes on the outside, and we'll just go. And just so we recap how to do that, let's do it that way first, and then we'll do the synthetic as well. Because when we get to 6 and 7, we're going to have to do long division. Right? Because for synthetic division to work, remember, it's got to be linear in the denominator with a leading coefficient of 1, if you want to use it exactly. Okay. To do polynomial long division, take the first number from the inside, first term, and the first term from the outside, and divide them. Right? And so in my mind, I'm doing x squared divided by x and figuring out what that is. Well, that's just x. So I line that up over the x term so that everything eventually will all be lined up when I'm done. And then multiply it together. X times x plus 5 is x squared plus 5x. Subtract straight down. See what you get. So those will always cancel if we're doing it right, which they do. X minus 5x, negative 4x. And then bring down the negative 3. And then do it again, right? Take the first term from the inside, first term from the outside, and divide them. And see what you get. I know it's been a while since we've done some long division, so I wanted to bring that back for sure. Negative 4. So I'm going to line that up right there. And then I multiply. Negative 4x minus 20. And I'll add straight down. So those cancel good. Positive 17. And our oblique asymptote, our slant asymptote, is always going to be y equals whatever that is. Okay, the quotient, x minus 4, but without the remainder. Whoa. Slippery. So y equals x minus 4. And just so you believe it, let's take a look at that one. Now, that's the only one I'll do for now. But y equals, what was our original function? X squared plus x minus 3. You gotta put that in parentheses. X squared plus x minus 3 over x plus 5. Yeah, right. So it kind of looks like in this regular, this kind of small window that that's the whole thing. It's not. Be careful. There's a lot more to this function than meets the eye when we're just looking at that negative 10 to 10 kind of window, okay? It's not just that. There's more to this function. Now, when we graph these, I'll make sure that our functions are pretty kind of close to the origin when we do it. So take a look at this line, y equals, was it x minus 4? There it is. All right? A graph that the line approaches, the function approaches, but never actually going to reach. Okay, not at the end. Just wanted to give ourselves kind of a direction to point that red graph with those arrows. Okay, it's really cool that it works out that way. And if you want to know how far away these are from each other, remainder. 17 over x plus 5 is going to be how far away they are, which is crazy. Right, there it is. Perpendicular to the x-axis, that distance right there is exactly 17 over whatever x plus 5 is at that spot, which is nuts. Okay, cool. Just wanted to strip that to you. Nice. Okay, and if we did it the quadratic division way, 1, 1, negative 3, bring it down, multiply, bring it down, multiply, bring it down. There's x minus 4, right? Because there's the remainder. I don't care about that. That's why from the beginning I told you just kind of leave that off. We don't need that when we're talking about the actual results. It's going to come in really nice if you remember. Okay, so this is quadratic, so it's only going to go down 1. So x minus 4. There it is. Okay, so I don't care which way you do it. If your denominator is linear, you can go with either one. I'm cool. All right, so there's number 5. Let's do a couple more to make sure we really got it. Let's go over there so we got some space. Because this one, with 6 and 7, we have to do it with long division. Not what I always want to have to do. If I can avoid long division, I like to, because it's just so much more work. But if we got to do it, we got to do it. Come with me. Let's see if I don't break anything. Let's see. You guys are famous for a second there. All right, number 6. Okay. If we want to figure out where this thing is headed, we have to divide. And so when we do polynomial long division, we want to make sure that we've got a spot for everything. On the inside, okay, it's cubic, and it's cubic, quadratic, linear, constant. Good, I don't add anything. 2x cubed plus x squared minus 4x minus 1. And the denominator is quadratic, and it's got a term for everything. X squared plus x plus 2. Good. Setup looks good. And now kind of in my mind, what I'm doing, and maybe you write it down because it makes it easier for you to see, I take the first term from the inside divided by the first term from the outside. See what I get, I line it up. So 2 over 1 is just 2, x cubed over x squared is x. So I've got 2x, and I line that up over the x. Then I multiply that result times the whole denominator, and I put it underneath. So 2x times x squared, 2x cubed, plus 2x squared, plus 4x, and subtract. First terms should cancel, which they do, so we know we did it right. Negative x squared minus 5x, and bring down that minus 1. And then do it again. X squared, sorry, negative x squared, right, over x squared. First term from the inside divided by first term from the outside. Negative 1. And really, I'm done. I mean, if I really was dividing here, I'd have to keep going, but I don't care what the remainder is. That's what I've got. I'll keep going just to finish it up, but there, like, y equals that? 2x minus 1. Let's just do it. I mean, we're here. Doesn't take that long. Negative 4x. Plus 1, yeah. Cool. That doesn't matter. That part doesn't make a difference to me. For me, when I talk about my slant asymptote, SA or oblique asymptote, OA, either one's fine, y equals the quotient, 2x minus 1. It's all about that right there. Graph it. Look at it. Plug in the function, plug in this. You want to see it get closer and closer. And it will. Guaranteed. If you're doing this right. So it's just so cool that it works out that way. It does. Okay. Now, just for a second, before we do number 7, degree on top is larger, so we had to worry about the slant asymptote, so we did our thing, right? Degree on top is larger, so we did our thing with division. What was the difference, though? Like, the difference in degrees, how big is that number? 1, right? What about here? 1 degree. Look at the degree of your slant asymptote. 1, the difference, right? But look at number 7. Degree on top is 4. Degree on bottom is 2. What's the difference in those degrees? 2. Which means that the degree of your asymptote, number 7, is going to be 2. So, and we're not going to do these where I actually make you graph them, because with number 7, you have a quadratic asymptote. And you're going to see, we're going to graph it. It's crazy that when we like point our arrows, and we're not going to do number 7 graphically. I would never make that by hand. Only do something like 5 and 6. But with something like 7, like you're going to see this function that's got asymptotes and holes potentially that are vertical and are happening at spots, but the slanted asymptote is actually curved, which is crazy. So if the difference was 3, your asymptote would be cubic. That's awesome. So, all right, cool. Let's just do it. Now, because your denominator is not linear, I can't do synthetic division. So I have to do long division. But when we do long division, just like synthetic division, you have to have a term for every spot along the way. And because your degree of your top is x to the 4th, you need an x to the 4th spot, an x cubed, an x squared, and an x, and a constant. You cannot leave any of those out or the results just won't work out. But if you look at the numerator, like there's none of them there. And so you're going to need 0x cubed, 0x squared, 0x, and then minus 1. Denominator is good. It's cubic, and it's got 3 terms. So we're good. All right, you're always going to have one more term than whatever the degree is, because you've got a constant, right? That x to the 0. So this is really the problem we want to try to do. And because the zeros are all there, it won't change the numbers dramatically, but we do want to have a cubic and a quadratic and all those spots, okay? And so I just do it again, right? First term from the inside divided by first term from the outside. Write it down if you like to. Don't if you don't. I'm okay with that, right? You don't have to. I know it's a little blurry up there. Hopefully you guys at home can see that, okay? And because that result is x squared, I line it up over the x squared spot. And then I multiply it all together. X to the fourth minus 2x cubed minus 3x squared. And now because we took the time to write all of those zero, right, coefficient terms, now we've got something to subtract from. All right, on good, 2x cubed plus 3x squared, bring it down, plus 0x. And do it again. First term from the inside divided by first term from the outside, 2x. Multiply it out, 2x cubed minus 4x squared minus 6x, and subtract. And just go straight down. 7x squared plus 6x. Bring down the negative 1. And do it one more time. I'm guessing you can probably finish that out. If you've got the handle on this so far, you're good. Really, I could have been done right there. That's all I really need is the quotient, but I like to finish things up so I know what I'm dealing with in case I really wanted to graph these things well. Call it a slant asymptote, call it an oblique asymptote. They are interchangeable, doesn't matter. I'm just going to switch it up just because why not? X squared plus 2x plus. And that's a fun one. I want to show you that one. It's so funky. Let's share the screen one more time. And then I'll just give you a chance to start working on some of these ones on your own. So folks at home, if you want to open up homework 2.6b, feel free to do that. And get started. X to the fourth minus 1. And what is it? X squared minus 2x minus 3. Okay. So like you look at just this, you whole function. Careful. Okay, there's a lot more going on here than you realize. And when I graph that, what is it? 2x x squared plus 2x plus 7. You can see that, I mean, they get so close so fast. But you've got this quadratic, the green graph, that is kind of that guide for what happens as these numbers get really big, which is so cool. Man, I love it. But don't worry about actually graphing those. We'll only graph rational functions whose degree on top, if it is bigger, is only 1 bigger. So we just have 2x minus 1, because just go to -1 and then up 2 over 1, up 2 over 1, and we can sketch those lines really easily. All right, sketching 2x squared plus x squared plus 2x plus 7, not as easy. And we still haven't found any points that actually exist yet. Okay, that'll be Wednesday, Thursday. Tomorrow we're off completely, okay, including me. It's a furlough day, okay? Every Douglas County employee had to take at least 2 furlough days to reduce their overall budget. And for us, tomorrow is one of those days. Okay, so I will not be doing any work. Okay, we're actually not allowed to work, okay, because we're not getting paid for it. So, so there you go. How do you feel? You feel like you're doing okay? Connor's into it. He's all about it. You guys are good? Okay. So what you're going to see with homework 2.6b, and we've got 10 minutes, so put a decent dent into it right now, is we start, 2.6a. 2.6b, there we go. I'll blow it up. Folks at home, you should be able to just pull it up yourself. Okay, is we start to do it all. Okay. All of the things that don't exist is all we're worried about right now. Okay. But added to this right now is a part E, describe the end behavior. What asymptote will the function approach as x approaches? That's that arrow. I want you to read it like that. Heads towards, right, positive, negative. But we got to do all the other stuff too, right? I want to factor and simplify. I want to be able to find the domain. Easiest way, just list the excluded values. I'm not going to ask you for the excluded values anymore. I'm going to ask you for the domain, write it however you want. But the easiest way, guaranteed, just list those excluded values. And I tried to kind of help you with how I wrote this out, right? Find the equation of vertical asymptote. These x equals some constant equations will be the zeros of d of x only. Find the coordinates of any holes algebraically. These will be the points x comma y, where x is a 0 of both the top and the bottom. And now we've got our end behavior, and that was today. Okay. So what I'm going to do is I'm going to start doing the work too. I want you to be able to look today to see that you're doing at least these first few correctly as you go. Okay. But this is on Canvas. So this is due tomorrow before midnight. So you got plenty of time to knock these 5 out. Okay. So I'm going to, I guess I'll just erase this for now, because if you've been looking at it for a few minutes now, or maybe I'll come up here. I'll erase these first. I'll move the camera so you guys can see. It's really more of an analysis thing, not a very complicated process. You just have to be able to factor and know what. Oh, there you go. All right, so ask questions if you've got any. I'm going to start to do some work. We'll give you some time on your own. But today is a good day to talk about stuff. All right. All right, looks factored to me, so that's good. So A, I'm just going to put check mark because it's done. Okay, B, X cannot equal whatever values would make the denominator 0. Let's do this. Domain. What I think you guys at home and everybody here should start doing, label what those parts are asking you to do, so that I shouldn't have to look at the instructions to know what you mean. Right? I put a check mark for A because it is factored and simplified, but like domains, this. Vertical asymptotes, that one. Holes, nothing. End behavior, I have a horizontal asymptote at y equals 0. Why? Because the degree on top is smaller than degree on bottom. Oh, let me stop sharing. Four is probably the hardest one on there in terms of factoring, because you have difference of cubes on top, and you've got something that I promise is factorable, but you're going to have to figure out the rational zero possibilities. Plug just the denominator in the calculator and find ones that work. Then synthetic division at least once to get you to a quadratic, because that quadratic will be factored. Okay? But to factor that denominator, factoring by grouping isn't going to work. You're going to have to just look at that denominator, which makes 4 that much harder. Everything else shouldn't be too bad. I'm guessing it's h of x. What's number 3? If you don't get something, you got to start asking questions, because we're a week or so away from the second half of chapter 2 tests. And we're going to start and finish chapter 3 before Thanksgiving. Did I type wrong? Something's wrong. Something's wrong with 4. So I started to piece them together in a separate one. This is something else, but yeah, maybe it was back here. No, that's not it. Why is that off by a little bit? I forgot. I just gave it 3 nice zeros, and one of them was x minus 2. What I thought I did x plus 1, and like x got to be minus 3, because that would have been x squared minus x minus 2 times x minus 3, x cubed minus 4x squared minus 3 minus 2 minus 5x plus 6. I don't know. I'll fix number 4. I don't know why I don't know where I'm messing up. X cubed minus 3x minus another minus 3x minus. I'll fix it for sure. It'll be done here in the next couple minutes. But take tomorrow, finish this up. Obviously, number 4 is going to be the tricky one to factor, because obviously I'm screwing something up. But I will see you Wednesday. Thanks, everybody. Questions at home? Wait for me to fix number 4 before you do it. I don't understand. Did I type it in the calculator wrong? X cubed minus 4x squared minus 5x plus 6. No, it should be. Well, no, on top it's minus 8, but on the bottom it's plus 6. I don't know. I'll figure it out. Thanks, everybody.